Sudbury, Ontario was, at its peak, the single largest point source of industrial pollution on the planet. 100 years of nickel smelting had stripped the landscape down to blackened bedrock across 17,000 hectares, ground so barren that in 1971 and 1972, NASA flew Apollo astronauts there to train for the surface of the moon. In the summer of 1978, 174 unemployed teenagers started hauling 50-pound bags of crushed limestone up those same blackened hillsides by hand. They weren't environmental engineers. They were part of a municipal jobs program built to keep laid off miners and students employed during a 9-month mining strike that had gutted the local economy. The material they spread was agricultural lime, the same cheap calcium powder dairy farmers use on acidic pasture. What that lime triggered when it hit the soil was a chain of consequences nobody fully predicted, one that ran far beyond chemistry and far beyond anything the program was designed to do. This is how bags of crushed rock rebuilt the most polluted landscape in North America. The Sudbury Basin sits about 400 kilometers north of Toronto, carved into the Canadian Shield, some of the oldest exposed rock on Earth. Roughly 1.85 billion years ago, a meteorite struck this spot with enough force to create the third largest confirmed impact crater on the planet. The collision cracked the crust and seeded the basin's margins with one of the most concentrated deposits of nickel and copper in geological history. Mining started in 1883 after a railway blacksmith noticed rust-colored rock in a blasted cut. Within 2 decades, Sudbury was producing 80% of the world's nickel, a metal that fed directly into armor plating and munitions through 2 world wars. The process that destroyed the landscape was crude and cumulative. To separate nickel from sulfur-rich ore, mining companies clear-cut the ancient pine and spruce forests, stacked the ore on enormous beds of timber, and set them on fire. These open roast yards burned for months at a time, releasing concentrated sulfur dioxide at ground level. Over the course of the 20th century, the smelting operations pumped roughly 100 million tons of sulfur dioxide into the atmosphere. At peak output in the 1960s, the annual number reached 2.5 million tons, roughly 4% of the planet's total sulfur emissions from a single city. The sulfur dioxide combined with moisture to form sulfuric acid, which rained down on everything in range. Soil acidity spiked to extreme levels. It comes down to one variable. When acidity crosses a certain threshold, heavy metals that have accumulated in the soil, copper, nickel, aluminum, stop sitting inert and dissolve freely into the soil water. Any seed that germinated had its root system chemically burned on contact. Without roots, the thin topsoil eroded off the steep hillsides during every rainstorm. Without topsoil, seasonal freeze-thaw cycles cracked the bare ground open and mechanically pushed out any seedling that tried to establish. Every spring, wind picked up the loose surface material and drove choking dust storms through the city. Each failure reinforced the next. The landscape was trapped in a loop that actively maintained its own collapse. In 1972, the mining industry spent about $160 million in today's money building a 381-meter concrete chimney called the superstack, the tallest freestanding structure in the world at the time, designed to push the emissions high enough to clear the local air. It worked exactly as designed. The ground level smog thinned, but the superstack didn't remove the pollution. It exported it across the continent, contributing to the acid rain crisis that would eventually require an international treaty to resolve. And it changed nothing about the ground. 3 years later, a local businessman planted 5,000 white spruce seedlings directly into the barren soil. Every single one died. The problem wasn't that the land had been damaged. Damaged land recovers. The problem was that the soil chemistry had been reorganized into a system that actively rejected life, a sealed loop of acid, dissolved metals, and erosion that tightened with every passing season. The man who identified the exact failure point was Keith Winterhalder, a botanist at Laurentian University who had spent years analyzing the chemistry that killed roots in Sudbury's soil. His conclusion contradicted every prior approach. The soil didn't need to be excavated, turned over, or replaced with imported fill. The millions of tons of toxic metal in the ground didn't need to be physically removed, that would have been impossible across 17,000 hectares of steep, fractured rock. The metals needed to be trapped where they sat. The logic runs backwards. The copper and nickel were only toxic because the extreme acidity kept them dissolved in the soil water. Raise the acidity back toward neutral, and those same metal ions would drop out of the water and solidify into inert chemical forms, still present in the ground, still measurable, but locked in place, unable to reach root cells. The tool was dolomitic limestone, a calcium and magnesium-rich rock. Applied at 10 tons per hectare, it neutralized the acid and flooded the spaces around plant roots with harmless calcium and magnesium ions that outcompeted the metals for binding positions. Metal availability in the soil dropped below 1%. The ground shifted from lethal to survivable without a single cubic meter of contaminated earth being moved. 10 tons per hectare sounds like heavy machinery. In Sudbury, it was 50-pound bags hauled up blackened rock on human backs. The steep, fractured terrain of the Canadian Shield wouldn't support equipment. Everything reached the hillsides on foot, limestone first, then a high-phosphorus fertilizer to replace nutrients the acid had stripped out, then a seed mix of fast-growing grasses paired with legumes that pull nitrogen from the air and feed it into sterile mineral ground. The economic crisis made it possible. In 1978, nickel prices crashed globally. Thousands of workers were laid off. 11,600 walked out in a 9-month strike that drained 22 million hours of labor from the local economy. The city created a summer employment program, and 174 students became the workforce for what would grow into one of the largest community restoration projects in history. They spread the limestone, seeded the limed ground, and within the first growing season, on rock that had supported nothing alive for a century, grass appeared. That was the expected result. The first surprise came from a deliberate gamble Winterhalder had built into the protocol. The seeding rate was set to produce just 24 to 40% ground cover, not a lawn, a patchwork full of intentional gaps. Those gaps created sheltered pockets, tiny zones where wind speed dropped, moisture lingered, and temperature swings softened. Into those pockets, carried on the wind from forests beyond the fallout zone, came seeds the team hadn't planted: paper birch, trembling aspen. Native species that would have died instantly on raw toxic rock, germinating instead in detoxified shelter that hadn't existed 6 months earlier. The limestone hadn't just allowed planted grass to survive, it had reopened a corridor for natural colonization that the acid had sealed for 100 years. And that corridor was about to carry far more than birch seeds. The spontaneous arrival of native trees changed what the project was. It had started as a way to keep teenagers employed and reduce the dust storms that choke the city every spring. The birch saplings pushing through the grass turned it into something different, evidence that the ecosystem had been held in suspension by the acid lock, waiting, ready to cascade the moment the chemistry was corrected. The grass roots, shallow as they were, bound the loose mineral soil in place. The chronic erosion that had been stripping the hillsides for decades slowed and stopped. The grass canopy, sparse though it was, insulated the ground surface against the seasonal freeze-thaw cycle that had been cracking the earth open and ejecting seedlings every winter since the 1880s. For the first time in a century, a planted tree could survive its first cold season. With the chemistry fixed and the frost heaving broken, the city scaled the program. In 1983, crews planted 228,000 bare root conifer seedlings into the stabilized ground. Survival rates ran above 97% on the same terrain where 5,000 seedlings had achieved 0% just 8 years earlier. Red pines grew 20 to 50 centimeters per year. The birch that had colonized naturally filled out half the canopy in treated zones. Over the next 4 decades, the program planted over 10 million trees by hand across 3,500 hectares. For context, the total cost of that 40-year effort was roughly 38 million Canadian dollars, less than a quarter of what was spent building the superstack, the chimney that relocated the pollution without fixing anything. As the canopy closed, leaf litter accumulated on the surface for the first time in living memory. The decaying organic layer brought the soil's basic living machinery back online, the organisms that break down dead leaves and cycle nutrients through the ground. No one needed to haul another bag of fertilizer up the hill. The forest was feeding itself. But by the 2010s, researchers looked more carefully at what had grown beneath the trees. The canopy was healthy, the trunks were strong. Underneath, the forest floor was bare, no mosses, no understory shrubs, no advanced fungal networks threading through the deeper soil. The pines stood in rows like a plantation. A functioning boreal forest has layers: ground cover, fungi, invertebrates cycling nutrients and retaining moisture. The planted zones had almost none of that. The limestone had fixed the chemistry. The trees had been planted, but the slow building biological architecture of a forest floor, the part that takes centuries to assemble naturally, was missing entirely. Ecologists found a workaround. Nearby forests scheduled for destruction, highway construction, mine expansion, still had intact forest floors. Workers cut out blocks of living ground roughly 2 feet square and 4 inches deep, complete with dormant seeds, root networks, fungi, and invertebrates. These biological plugs were transported into the sterile plantations and set at regular intervals. The transplanted patches began spreading outward from their plots. Understory plants crept beyond the edges. Fungi colonized surrounding pine needles. The chain needed one more deliberate link, and this one couldn't come from a bag. None of it was seamless. On the steep hillsides, the iconic blackened ridges that had defined Sudbury's silhouette for decades, heavy rain and snowmelt washed the limestone downslope before it could fully neutralize the rock. Those crests stayed dark, greening slowly from the bottom up, trapped in arrested recovery. After 45 years of continuous effort, the program has treated roughly 3,500 hectares. The original barren zone was 17,000. That is 20%. And then the data came back from the water. Parallel to the terrestrial recovery, industrial regulation had forced sulfur dioxide emissions down by 95%. With the acid source cut off, 7,000 damaged lakes across the region began flushing their accumulated acidity. Dissolved aluminum concentrations dropped, and into that recovering water, without any human stocking program, came the lake trout, a species wiped entirely from the basin, now confirmed in at least 32 lakes where it had previously been eradicated. On land, the maturing forest created habitat where none had existed. Black bears moved in. White-tailed deer established permanent herds. Sandhill cranes nested. Over 80 bird species and 16 mammal species now hold permanent territory on ground that supported zero terrestrial wildlife within living memory. Crushed limestone neutralized the acid, neutral soil locked the metals in place. Locked metals let grass germinate, and grass stopped the erosion that had been stripping the hillsides bare. Stable ground let trees survive their first winter, and the trees over decades rebuilt the soil biology underneath them until the system ran on its own. Across 7,000 lakes, the parallel drop in emissions rebuilt aquatic food webs that had been dead for decades. In 1978, 174 students spread crushed rock on bare ground as a summer job. The ground they walked across was so lifeless that Apollo astronauts had trained on it to study impact geology identical to the lunar surface. Today, over 10 million trees stand on that ground. More than 250 species of plants have been documented across the treated zones. The new forest has added over 1.1 million tons of biomass to the landscape and locked roughly 500,000 tons of carbon into a system that was previously a net carbon source. Sulfur dioxide emissions from the basin are down 98% from their peak. Lake trout swim in 32 lakes where the species had been eradicated. Comparing the same coordinates over time, the image on the left is from the 1970s. The one on the right is 4 decades later. The blackened bedrock has become dense, closed canopy forest. The chain is still running, and it remains fragile. The original limestone application is slowly leaching from the oldest treated sites. Below the surface, deeper soil layers remain highly acidic. The forests are healthy, but they grow on a chemically neutralized veneer, one summer of human effort that may require centuries to mature into true geological topsoil. Millions of tons of reactive mine waste still sit in containment across the basin, requiring constant management to prevent a secondary acid release that could restart the collapse loop in reverse. One patch of ground near Baby Lake was deliberately left untouched, black, barren, biologically sterile, a permanent control site and a record of what the entire region looked like before anyone opened the first bag. In 2019, Jane Goodall traveled to Sudbury to plant the 10 millionth tree. It went into soil that 50 years earlier NASA had used as a stand in for the surface of the moon. The 381-meter superstack, the tallest chimney ever built, the monument to the idea that you solve pollution by making it someone else's problem, is being taken apart right now, piece by piece, scheduled to disappear from the skyline by 2029. The trees planted by the program it failed to replace are still growing. Sometimes the most effective engineering isn't the tallest structure you can build, it's the simplest reaction you can set off in the ground beneath it. If this kind of project interests you, where one fix, placed at the right point in a broken system, unlocks a chain that no budget could have built directly, subscribe, and I'll see you on the next one.